Uriarte Andrea, eskerrik.
Thank you very much, Ms. Uriarte. And now we're going to continue with our next keynote lecturer. Dario Gil leads the largest quantum computing laboratory in the world. He's Vice President of IBM and Director of IBM Research, a research division that works to develop quantum computing. IBM Research has more than 3,000 scientists spread across 12 laboratories on 6 continents. Its aim is to spearhead the computing of the future, marked by advances in artificial intelligence and quantum computing. The title of his lecture is The Future of Quantum Computing. So please welcome Dario Gil.
Arratsaldeon.
Arratsaldeon. Good afternoon, everyone. Right, while I connect up my computer, I would just like to say how extraordinary it was to see this decades-long investment in science and technology that's been going on here in the Basque Country. We are delighted to form part of this history and to talk about what's coming next in this revolutionary world of quantum computing, which is what I'm going to be doing this evening in my talk. My name, I am the Director of IBM Research, which is an institution within IBM. IBM itself has been around for over 110 years, and it's been working in the world of computing and information technology for all that time. And in fact, in the world of computing, it's been working for the last 80 years in the private sector, working to push forward the boundaries of artificial intelligence and quantum computing as well. And we are working here in the Basque Country with our colleagues here, and hopefully we're going to be pushing forward this frontier even more. Now, first of all, let me just show you where I work. This is the research headquarters of IBM Research. It's 45 minutes north of Manhattan in the city of New York. It's a beautiful place, which was designed by Aido Saarinen in 1961. He was also the architect who designed Bell Labs. You might have heard of that. And it forms part of a global network. I can just show you some of the buildings, including that. We have a lab which focuses on artificial intelligence. We work in collaboration with MIT. We have Almaden in California. We have a lab there. We also have one in Zurich, where they're having breakthroughs in the world of nanotechnology. In Albany as well, we have another lab where we focus on semiconductors mainly. So this technological and scientific community, along with our collaborators and partners all over the world, dedicate our lives to imagining the future of information. So to understand what's happening in quantum computing, it's important to go back to the beginning of information, the beginning of the digital world. And when exactly was that? Well, I think it was something that this gentleman defined very well, Leibniz. Now, he was an important philosopher of the Renaissance, but he was also the co-inventor of calculations along with Newton, who developed it independently, or the calculator, sorry. Now, he said that in the very, very beginning, only the binary world existed. That's what he said. Now, of course, in Renaissance, they were very keen on logic, so he was trying to show that. So he had an intuition about the binary nature of the early world, and he tried to show that in a mathematical way. And then Claude Shannon, in fact, did it in the 1940s. Now, Claude Shannon was an important mathematician, and he was the person who defined on a theoretical nature, the nature of information. He said that information is the resolution of uncertainty. So he introduced in popular vocabulary the idea of a bit, a binary digit. And it was from that moment on that in society we started to understand that very, very different, very complex processes, for example, DNA or the old perforated plaques that we used to find in computers, have a very different representation. But they have something in common, because what they have in common is that they are all means of processing information. So he created a unified system of how we can see the world through information, and we've been able to generalize that in very, very different areas and very different spaces. Now, this theoretical idea of the digital, that we can theorize the complexity of the world using zeros and ones, was complemented from a technological point of view by the advent of semiconductors, a transistor in 1957, and the implementation of what has been called the Moore's law, which is the ability to create transistors and to double the number of transistors that we can actually put on a silicon wafer every 24 months, more or less. This process of exponential growth was predicted by Gordon Moore. In fact, he just died, I think, passed away 1 year ago. He was one of the founders of Intel. He made this observation in the 1960s, and he simply just was thinking, it was just a measurement, and he said that the number of transistors that were being manufactured in industry would double every 18 months, 24 months, more or less. And with these 4 points, he extrapolated this information and said, this is what's going to happen. We're going to continue with this exponential growth. And in fact, that's what's happened. And it has happened over many decades. And this is how we've digitalized the world. Bits now are almost free. And today we have different systems, computing systems and computers with a very, very high computing capacity. Just to give you some examples, in a current chip, we can include more than 22 billion transistors in a chip that's really just the size of my fingernail. And we can process more than 20 billion transactions every day. And in terms of supercomputing, which is what we do at IBM, we can process more than 200 trillion, I think that means, calculations per second. So, if we look at everything that we have achieved, we're talking about the collaboration of hundreds of thousands of scientists all over the world, and we've been accumulating this technology over decades, and all of this has brought us to where we are today. Now, the world of semiconductors and the advance of the integration of information is going to continue in the future. And last year, we've seen, in fact, a new generation of transistors which are going to enable us to extend Moore's law over the next decade and perhaps even further. So if we look at this situation, which is a very, very brief overview of what's happened over the last few years in the world of information, but once we've done that, we need to stop and think about what is the true nature of information and whether there are possibilities that go beyond the world of bits, zeros and ones. So the intersection of mathematics and information was what gave rise to the world of bits. It's the intersection of physics and information, again the same ideas, that enables us to come up with a new concept, which is the world of qubits, and that's the quantum world. So in this case, to start and to try to explain this idea, let me just tell you that we're not just limited to zeros and ones. This is what it means by having qubits. There we are. On the left-hand side, you can see a graphic representation of the digital world, where we imagine a sphere or a circle, and we can decide whether it will be the pole will be facing north, in which case it will be a 0, or if it will be facing south, it will be a 1. But in qubit, we can have superimposed state. So we have a sphere, and we can put the red dots at any point around the circle. We can put it around the equator, for example, and where we can have a linear combination of zeros and ones. So the first thing that we're able to exploit with the use of the quantum world is the creation of superpositions, which will, and we're going to also combine that with the idea of entanglement, and I'll explain what entanglement is in a minute. So this revolution of how we represent information, and the really interesting thing about it is that we shouldn't understand quantum computing as just an extension of classic computing. It's not just an extension of Moore's law. It's much more than that. Actually, for the first time ever in the world of computing, we're seeing a branching out. The whole progress is dividing into two branches, and the future is going to be the combination of classic computing that we all know and we all use, combination of that with quantum computing, which is going to offer a series of capacities which are simply not available in the classical world. And what are those possibilities? Well, now, classic computers are very advanced, but from the point of view of complexity, they only enable us to resolve simple problems. Now, I'm not saying that they're simple for us, but they are simple in the sense that the number of variables present in the calculations that we're going to be using doesn't grow exponentially, doesn't increase exponentially. Now, we might be asking ourselves, well, what? Do we have problems in the world in which the number of variables is exponential? And the answer, in fact, is yes. There are many problems that are really important in the world, including the simulation of nature, for example, physical process, chemical processes, processes of optimization, and mathematical problems that are really important, for example, factorization, in which the number of variables that we need to calculate using classical computers is exponential. And therefore, it's not feasible to do it with classic computers. And the only thing we can do is to have an approximation of the solution. Quantum computing is the only technology that we know that actually makes it possible to calculate in a very precise manner these types of problems, rather than just having approximations. Let me just give you an example. The first example is the problem of factoring. Now, factoring is very important because that's the basis of encryption in our digital world, in our digital environment. For example, if we want our bank to be reliable and have no one to be able to intercept the transmission of banking information or medical information, for example, we want to encrypt that information, then what we do is we have an encrypted program in which we have two private keys, which will be the P and Q. They're two numbers, P and Q. They're private numbers, and the product is the public key to which everyone has access. Now, this is a really important problem in a world. And in one direction, multiplying two numbers, that's really, you can do that with a classic computer and it's very efficient. But if you have a quantum computer doing that, it's really slow compared to a classic computer. So in this context, a classic computer is able to multiply two numbers much quicker than a quantum computer. But if we go in the other direction, if I give you the product, so for example, so we have 2, 3 and 5, and the product is 50. Now that's very easy to do from a classic point of view. But if I give you the product, so in that case it's 15, and I say, well, what two prime numbers will end up give you that product, then it's very, very difficult to actually calculate that using a classic computer. So it's actually quite asymmetrical in this case. So in this case, a quantum computer can solve this problem exponentially more quickly than a classic computer. So the question is a quantum computer better or quicker than a classic computer? The answer is, well, it depends. If we get the right problems, if we select the right problems, then we can have exponential advantages, but we have to choose the problems correctly. Now, this exponential advantage is due to a very important property in the quantum world, which is called quantum entanglement. Now, this is perhaps one of the most sophisticated ideas within the field of quantum physics. It's not easy to explain, but I'm going to try to do that. And I'm going to do an experiment. I'm going to tell you about an experiment that was actually carried out last year with a Nobel Prize laureate, and hopefully will shed some light on the possibilities of quantum entanglement. Schrödinger defined quantum entanglement as the best possible knowledge of the fact that the best possible knowledge of the whole does not necessarily include the best possible knowledge of its parts. So just by describing all the different parts individually, that doesn't enable us to understand the whole which is reflected by this type of quantum entanglement. So I'm going to do an experiment now, and I'm just going to tell you a little story so that you can understand what's happening, and then we'll see the result. Don't worry too much about what's happening here. Don't worry, I'll explain it in a minute. I'm going to launch a program which is going to interact with a quantum computer in New York, and it's going to generate a result, and then I'll explain it. Right, let's just get this going.
Aquí estamos con dos qubits haciendo un entrelazamiento y voy a lanzar este experimento.
Okay, right, let's get this experiment going, and then we'll come back to it in a minute. Right, let me explain this experiment. Right, in this classic computer, we had a program, and we've launched the program. We started to run over the internet, and it's going to a quantum computer which is in New York. Now, these 2 ones and zeros have been converted into microwaves, and they are moving through a series of cables, which are cryogenic cables, to the quantum processor, which is working at a temperature of 15 millikelvins. It's really, really cold, very cold. In this quantum processor, the process of information is happening. We have quantum entanglement and interference, and they're the keys of quantum computing. And this experiment now is running, and when it's finished, it'll give us a result. Now, physically, this quantum computer, and what we can see here is a series of pictures of it. They're beautiful machines, by the way. They're absolutely gorgeous. There you can see the cables through which these microwave pulses travel. The square at the bottom, which is like a mirror, is the quantum processor where the qubits are. And this is when we're going to amplify the signal and extract it in order to see the result. So what's the experiment that we're doing? Where does this idea of quantum entanglement, where does it come from? Well, we're going to just generate an idea. And this idea is the following. Imagine that we have 2 particles. Now, there could be 2 photons, there can be 2 particles of light, 2 electrons, etc. In our case, they're going to be 2 qubits. But we have 2 particles. That's what I want you to understand. 2 particles. And when they're together, they establish this property that we're trying to describe, entanglement. And then we separate these particles. It can be to any distance. For example, they can be separated to either end of the universe. But once we separate these particles, if we observe just one of them independently, we would see that it just behaves randomly. Just to give you an example, or to give you for example, to give you a metaphor, it's like having a coin. The coin can be heads or tails, and when it's being spun on a table, it's in a random state, and it'll then end up being either noughts or crosses, or heads or tails, sorry. When we have the particles and they are entangled, and we can look at them as a whole system, the relationship between them isn't independent. And what does that mean? It means that when we measure, for example, the state of one of the particles, its position, or if it were a coin, whether it's heads or tails, then we would know immediately that the other particle, no matter where it was, whether it would be heads or tails as well. And this is really surprising, because in this case, just imagine that we have 2 coins that were entangled, and when we would measure them simultaneously, when one is heads, the other will always be heads, and one is tails, the other one will always be tails as well. Now, this just violates a really basic principle that is, really at the heart of our intuition, which has to do with causality. It's very freaky. Now, it's not very intuitive, this idea. But this idea, well, Einstein and his collaborators in the 1930s, they thought that it wasn't quite complete. There was something missing. They said, that's impossible. That's impossible. There's something wrong here. There's something that we don't know. there can't be information present in this. There must be something there that quantum mechanics isn't taking into account. So they said literally that quantum mechanics isn't telling us the whole story. There has to be something else that will be able to explain this perfect correlation between these two particles at that distance. And it can't be that we're just, violating the principle of causality.
In the 1960s, a researcher, a mathematician, Daniel Bell, suggested something. He took this idea very seriously, and he created a whole series of equations to prove whether Einstein, Podolsky, and Rosen were right or not. And he created a number of inequalities, and he created an experiment. If we measured it, we would know if Einstein was right or not concerning this idea of the fact that there were hidden variables there. Over the next decades, a whole series of physicists created a number of different experiments with different systems as well to precisely prove or carry out the experiment suggested by Daniel Bell. And they last year they won the Nobel Prize for Physics. So if we measure these two photons that are entangled and then separated, the measurement of the correlation between these two particles, according to Daniel Bell, if Einstein was right, couldn't exceed these pink strips you see there. If Einstein was right, the dots that will be measuring the correlation of particles would not reach this pink strip that we see here. So the experiments that were carried out by these physicists proved clearly that Einstein was not right, and that this type of charts proved clearly that this was the case.
Conclusion.
Now let's look at the conclusion of our experiment. An experiment we've carried out in a quantum computer in a few minutes. This is a story that took 70 years, right, of work, 70 years of work and effort. And the demonstration that these principles of quantum entanglement are real, they reflect reality. This is something we can carry out in real time with a new quantum technology that is available. And this quantum technology has a feature to it that it has an exponential power, where the number of present states in the quantum computer is 2 to the power of n, where n is the number of qubits. Which means that when we have a quantum computer of more than 100 qubits, the number of possible states there would be 2 to the power of 100, which is more atoms, represents more atoms than the ones we have on planet Earth. Which means that to represent the state of information present in a quantum computer, we would need to use all the atoms of planet Earth to store ones and zeros. So when we have more than 280 qubits, quantum bits, we would need to use all the atoms of the universe to be able to represent that. And in fact, in this technological trajectory, we're already creating quantum processors that exceed these figures. We've, in fact, last year we announced a quantum computer with 443 qubits. So this is a process of technology that's moving forward thanks to a scientific and technological effort. We can not only create quantum bits, not only can we entangle them quantically in a quantum manner, but we can also create systems that work, as we have proved so far with large dimensions. And this is a very special moment. Inside these quantum computers, the device that would be equivalent to the transistor in the world of microprocessors, in this case we use a technique, a device that is based on the principle of superconductivity. It's 100 nanometers by 100 nanometers, and it essentially enables us to create a virtual atom with 2 very well-defined states, which enable us to create not just qubits, individual qubits, but also we can entangle them with each other. So the future, what about the future? The future of computing is going to be about the combining classical computing, transistors and semiconductors, with the quantum computing. And the systems that we are creating are based on the idea of parallel quantum processors that are going to be connected to each other, first of all with classical information and then very shortly with quantum information. And then we're going to be creating large systems that will make the most of the extraordinary calculation or computing capability of high performance computing with quantum processors that have very special laws to them, with this exponential capability to solve specific problems that we will not be able to deal with in a classical way. And here we have the aerial quantum system too, that we are now building in the US, and we're going to be having the first system operational by November 2023, in a few months' time, really. And this reflects the idea that I talked about. We have a number of different classical and quantum processors working together. We have designed these systems in a modular way so that we can expand and create large quantum computing systems, and we anticipate in the future they're going to be having more than 100,000 qubits working together. And we're going to be able to face a number of different challenges here, because if we can simulate better nature, we'll be able to come up with solutions to some of the key problems we are now facing. We can maybe create new fertilizers to improve agriculture. We can have new catalyzing processes in the industry. We can also maybe make new discoveries in the world of physics, high energy physics. We can improve the batteries we need in the electrification of our transport system. Maybe we can also develop materials that are highly resistant to corrosion that we can use in aerospace and in our cars. We can also develop new drugs that can resist strains or new strains of bacteria. So if we simulate physical processes, will be better, and this is very much related to us moving forward as a society. Let me finish this presentation by saying that we're creating a new scientific community that is not just creating quantum computing, but also benefiting from it in order to carry out, to achieve new advances. In 2016, we used the first quantum computing in the cloud, and you see this the scientific community all over the world who started to create new programs, looking for solutions using that new technological capacity. This community has grown exponentially. There are more than 500,000 users now, and more than 2,000 scientific papers have been published using these technological possibilities, and it is this energy of researchers, teachers, students that think and believe that we can develop further all these possibilities in science. And let me finish my presentation by mentioning our collaboration, our partnership in the Basque Country with Basque One too. This is a new revolution. This is a new institution, a new system of partnership where we have professors, researchers, and industrial developers that we have in the Basque Country. Thank you very much indeed.